Hi everyone. I am going to start making weekly videos to go over some of the problems from each lecture because uh, if you miss them live, then that's kind of it. So we need another way. Week 11 slides covered center of mass and moment of inertia, so I'm going to do the one problem with the funky geometry and um, then talk about inertia conceptually, and then do some derivations to show you where the coefficients come from and how to set up the integral. Alright, so now let's try to find the center of mass of something with some funky geometry. The sum of all little pieces of mass and their distance from the center over the total mass. And so in this case, you can move this, I move this total mass over here. So let's consider if it were like just a solid circle. Then it would be, its center of mass would be equal to, and we're gonna break it into two parts. So you've got the part where the part that remains after you cut out that whole circular piece and that circular piece. So it's going to be equal to you adding that little circular piece and then the thing that it was cut out of. So I'm going to call the thing it was cut out of 1, like M1, whatever. And then the cutout 2. So I've got M1 x1 plus M2 x2. This x1 here would be the center mass of the circle with the cutout. So this is going to be your new center mass, and it's the one that you're actually trying to find, as opposed to this, which would be if it's a solid circle. So we don't know what M1 or M2 is, but we do know the areas because they give us that radius. So assuming uniform density, you can set up proportions for all the mass over the areas. Yeah, it's not mass over volume because there's no width or anything, so it's just a proportion, so that like negligible, doesn't matter. Solve for each of the masses and plug them in. So I solved for x1 first, which is the center mass of the thing with the cutout. And then I plugged in the expression for the mass, which would be its area times the density. So you've got area total times the density, blah, 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 and all the densities end up canceling out, so it doesn't even matter. Well, it does, but you know, it helps us, and then we can solve for x1. And you can easily find the areas. And then this was also on your quiz. So you can solve that one the same exact way. You can figure out those areas, and you could have assumed it was a solid square. Okie doke. The next slides get into moment of inertia. So we remember that inertia is the tendency of an object to resist changes in its motion, which is another way of saying it's an object's tendency to resist acceleration. So it's dependent on mass. You know that if something's heavier, it's going to be harder to get to accelerate. And then with rotational stuff, we've got moment of inertia. So that is the resistance of an object to changes in its rotational momentum. Alright, honestly, okay. Okay, demonstration. We have demonstration time. I don't have meter sticks, but I have 4 pens. So I added a lighter to the end of one of them. So this one is heavier, but it's got mass on the end of it. So if we dropped them like this, air resistance is negligible. Boom, they hit at the same time. Okay. We broke it. Okay. But if I drop them like this, I'll tell you if you didn't see. The pens with the mass on the end, far from the axis of rotation, fell second. So that means that unlike with me just dropping it like this and them hitting at the same time, this object, it resisted the rotational acceleration downwards more than these two light pens. Alright, different example. I'm looking at the slide with the hollow cylinder and the solid cylinder, and the question is which one wins the race. The hollow cylinder and the solid cylinder are the same mass, so that means that the hollow one must be made of a more dense material, so you can imagine the solid cylinder is made out of wood or something, and the hollow cylinder is iron, so we're making mass not an issue. So now we're able to just focus on the shape. So for the iron hollow cylinder, more of its mass is far away from the axis of rotation. The distance that a mass is from its what it's rotating around matters a lot, and is going to increase that moment of inertia a lot. So the hollow cylinder is going, because it has a bigger moment of inertia, it's going to resist change to its angular momentum more than the solid cylinder. So that's why it is going to lose the race. Okay, I'm going to talk about the equation a little more. You can take something that has a funky shape and take, so I have that little dot there, that's dm, so I'm going to take the moment of inertia of that little piece, that's all I want. So I set it up like this, which is just so then if you take the integral of both sides, you have I integral of r squared dm. Assuming we have a uniform density, we can say that it's equal to the total mass over the volume, and that little piece over its little volume is equal to that density as well. So solve for dm and you get dv rho, or density, yeah. And you can plug that in. And so this is the equation that I start all of my inertia derivations with. And we can do some examples now. So the main things that are going to change for each of these derivations are the bounds and the expression for the density and the dV, the little volume that you're considering. So in this case, the density is going to be equal to the total mass over the length. We are not considering any negligible width or anything. It's just a rod. It's like a very ideal object. And then our expression for dV is going to be, it's going to be a little piece along here. So I'm just going to say that it's dr. Times 8. So then 1/12, this cancels with, I guess I should do that. This cancels with one of these, so we've got 1/12 ml squared. And that's what we were expecting to get. So the density of this thing is going to be its mass over A times B, its area. Again, we've got like a negligible width there, or height, I guess. And then our expression for dV is to just consider something like this, like a little piece like this. So you're going to be adding up a bunch of these when you're doing the integral. So that would have the little dimension dr, this little thickness, and it's going to have times b. And b is a constant, so each of these, same. Then we can plug that in. And we're going to be doing it from a over 2 to negative a over 2 again. So you can kind of see why we're going to get the same thing. So then that b, since it's a constant here, it just cancels out. So, and then the rest of it is all the same. And that's why you get the 1/12. I'm looking at the cylindrical shell, which has a moment of inertia of mr squared. And I'm going to derive the moment of a hollow cylinder with any thickness you want, and see if we get the same result, and also note that it's the same as the point mass, so I want to see why. Okay, so then in this case I have this outer radius is R2 and this inner radius is R1, and so the density is going to be the total mass over that outer area minus the inner. Well, to find the area, we're going to do like that outer area minus the inner area to get that nice donut times h. Okay, and then for what we're going to integrate over, we're going to consider a bunch of little volumes of rings from different distances r from the axis of rotation, and they're going to have thickness dr. So that is why our dv is 2 pi r drh. And then I plug that in, and I get 2 pi r h. Oh my god, that's not a constant. We're again 2 pi h rho r1 r2 r cubed dr. Okay. So I'm going to ignore this little, well, okay, we have R4 over 4, and then we're plugging in R2 to R1. So we're going to have all this stuff. I'm plugging it in now, because I want to. R2 minus R1 squared H R2 to the 4th minus, yeah, R1 to the 4th all over 4. So we've got this. And so we know when we can factor this, so we've got something that's squared down here, and oh, those go there. Silly. Because it's pi r squared. Sorry. Okay, and then to get one of these to cancel, I'm gonna factor this. So this is the same as saying r2 squared minus r1 squared times r2 squared plus r1 squared. So the r2 squared minus cancels with this. And so then we're left with 2 pi, well, the pi's gone, 2m, h's are gone, r2 plus r1 over 4. So that's equal to 1/2 m r squared plus r1. And when we have a cylindrical shell, then R2 is going to be equal to R1. So when R2 is equal to R1, we are going to get 2r squared, or 2r2 squared, yeah. And so then the 2 is going to cancel with the 1/2, and we get mr squared for the shell, which is the thing that's on your on the table. That should I show better?
Helpful in some way, shape, or form. That was unnecessary, but I hope you enjoyed. You don't really have to enjoy it. I just hope it helped you.
Did
this is supposed to be
enjoy
an
it.
informative
Thank you.
video. Bye bye.
Bye.
Ciao. Thank you for watching. I'll see you in the next video.